Hello everyone. So what I want to do here is to show you the process of solving a physics problem. So we'll start with the kinematics problem. What you can do is just hit pause and just read the prompt of this particular problem, which I got from the OpenStax textbook. Read through the prompt yourself, just have some ideas of you might approach it. This is really important. Hopefully you took a moment to read through the problem for yourself, and we'll go through it together. This way you can kind of see what I'm thinking about when I'm trying to solve a problem. Notice when you're first starting off, it's good to spend a lot of time at the very beginning to just figure out what's going on. You don't have to jump to trying to solve this right away. And I think it'll help you in the long run when you take that time going very slowly in the beginning to understand what's going on. Okay, so there's a ball that has been thrown and it's caught by somebody with a mitt. Presumably this is kind of like a baseball game or something like that. But the particular details of the ball and the mitt, that's not really that important. What's going on, the big picture, is there's an object, the ball, and it's being stopped by something else, the mitt, right? So whenever you're reading a physics problem, even though there's a lot of details about what kind of ball and what kind of mitt, you want to think about, okay, is this really that critical to how to solve this problem? You're trying to find the big ideas, kind of general ideas that apply not just to the ball, but to planets and anything really, right? So in this particular case, okay, there's a ball and it's been caught by this mitt. Right away, what I like to do is just start off drawing a picture. I tell students this all the time, but there's some hesitation to always drawing a picture. Maybe it's because there's kind of an assumption of you have to make this very artistic, but when you're sketching something out for physics purposes, it could just be a circle, it could be a box, right? So in the case of the ball, here's a ball, and the mitt could be just something like that, right? So notice it doesn't look like a mitt, and that's fine. It's not really that important. So you might put some details like, okay, there's a ball and it's moving that way, right? And it's eventually going to hit the mitt and the ball is going to be stopped. So maybe you want to do kind of a before and after. So you can write a before and after. What happens to this is, let's say the mitt's still there and the ball's now stopped, right? Because the mitt person caught the ball. Okay, so the next part of this, right? Notice going very slowly. That's good. Don't need to rush through solving a problem. Once you get better and better at this, then you can go faster and faster. But it's at the very beginning. I think it's important to go slowly and just kind of process what's going on. So the ball decelerates, right? And then they give you a number by which it decelerates. That's an acceleration. So sometimes the word deceleration is used, but it's still acceleration, right? As the concept of it. So the ball changes its speed, really its velocity, but more on that later. But think of it as it has a certain speed and it changes, right, from something to zero, right, because it's moving initially and not, right? So it has some velocity or speed. Let's keep it using speed, and it stops, right? So it has zero speed after some time has passed. So they list some time, and that's the time it takes for the ball to actually come to a stop, right? So if you film one of your friends throwing a ball and somebody catching the ball, and you record this, you can play back the video and see that the ball doesn't just stop instantaneously. It takes some very, very, very small amount of time for the ball to actually stop, right? Okay, so there's a certain amount of time that takes for the ball. It takes the ball for a certain amount of time for it to come to a stop, right? Okay, so we don't know what this initial velocity, right, or the speed and of the ball is. We don't know what the initial velocity is, so what we're going to do is try to figure this out by what's given, right? So I kind of know now what's going on before I even look at an equation, before I even think about these numbers. I kind of have a rough idea. I've sketched out what's going on. There's a ball, it's traveling towards the mitt, and after some time, the ball comes to a stop at the mitt. Okay, so let's think about the big ideas that you can apply here. This is a kinematics problem, so what we're after here is to describe motion. That's what kinematics means. It's a fancy word for describing motion without really thinking about what causes motion. That comes later. So we are describing motion. We have certain concepts that we can put together, right? So the one important thing that we need to do here is to relate how velocity, acceleration, time all connect together. So if you have a change in velocity, right? So there's a final velocity and an initial velocity. If there's a change in velocity, using the definition of what an acceleration is, we can write that this change in velocity is caused by an acceleration that is applied over a certain period of time. Okay, so this initial velocity would not change if there was no acceleration. And because there's an acceleration, that initial velocity is changing by some amount, right? And that's the acceleration that's causing it to change. Okay, so this is kind of the key idea here to apply to this problem. And how do I know that this is what I need to apply? I'm thinking about what's given, right? What I'm thinking about this, what's described in the problem, what's given to me to solve for what they're asking for, the initial velocity. I'm given an acceleration, I'm given a certain time, right? And I'm thinking about, okay, what relates all of this together? Now, you might not know this is the place to jump to, right? So maybe you think, where did I get this from? And if you ever forget that this is how it all connects together, you can always go back to definitions, right? So if you forget how velocity, acceleration, and all are connected together, you can say, okay, what is an acceleration in the first place? It is a change in velocity over time, right? And that's key to remember, because as long as you remember what acceleration is, then you can get this, right? You can come back to this. Why? Well, a change in velocity, right? A change in velocity is just final minus initial, right? Two different velocities. And a change in time, sometimes we use this interchangeably. A change in time you can just say is t, right? As using t as a duration. And so that's how they are related. So once you can remember this, right, that this is the definition, you can get to this equation, right? And that's a good thing to be able to do, just in case you forget, right? So you don't need to memorize a whole bunch of equations in physics, and it's encouraged not to memorize a whole bunch of equations in physics. But the idea is that you try to have a few key concepts and then get everything else, right? By kind of focusing on the key ideas, you can derive other relationships based on it, right? Okay, so given this equation now, let's see if we can solve this problem, right? And another thing to notice is I have not yet put any of the numbers, right? And when you're first starting off, there's a tendency to focus on the numbers that are given and immediately write that down or to put it into your calculator. I would encourage you not to do that till the very, very end, right? As you can see, I'm doing things symbolically. I'm not using the numbers that are given. So when I'm part of this, the exercise is to show you how I kind of think about a physics problem, just deconstructing the whole process so you can kind of see this is how I would think about it, right? So when I read the number, so if the deceleration of the ball is 2.10 times 10 to the 4 meters per second squared, right? That number, when I'm reading through it, I just kind of skip over in my head, right? I see it, but I kind of put it aside, as I'll come back to that later. I'm thinking of that number as a variable a, right, for acceleration. So start thinking in that way where when you see a number, your first thought isn't to focus on that particular number, but to say, okay, I'll use that as a variable, right? So and then when you use the equation, the variable is already there, and then at the very end, you can solve for what you need, right? Okay, so we're after the initial velocity, which is that right there, right? So the initial velocity is here. So what I'll do is solve for that, right? So moving some terms around. If I move the initial velocity to the right-hand side, okay, so I've solved for the initial velocity, right? So if you would like, maybe I'll move it over so it's easier to see. So the initial velocity is the final velocity minus a times t. The final velocity, we know what that is, right? So final velocity is 0, right? Because the baseball, or just ball in general, will come to a stop at the mitt, so the final velocity is 0. The acceleration, right? We have the number for it, but here's where you want to think about your signs, S-I-G-N, signs, for the variables that you're going to put in, right? So whether this number that's given up here is a positive number or a negative number all depends on you, really, how you set up the problem. And there's a lot of flexibility for you to pick the direction of things, right? So what I mean by that is this ball is moving, let's say, to the right, and we have to decide what that means. Moving to the right, does that mean positive? Does that mean negative? And what we could do, just to stick to what you're probably used to thinking about the x, y coordinate system being oriented that way. So to the right is usually considered positive. So we can just stick to that and consider the initial velocity to be positive going to the right. In that case, let's think about what that means for deceleration or acceleration. In that case, for this velocity that's positive to turn to 0, then this acceleration must be a negative number, right? It's because think about what would happen if the acceleration was positive. Then what that, by definition of what an acceleration is that the velocity would have to increase. But it's not increasing, right? It's not getting faster and faster. The idea is it has a certain velocity and it goes to 0. So that's why this acceleration should be listed as a negative number. And if you don't account for the signs correctly, you'll get something that doesn't make sense at the end, right? So that's a nice thing about problems in mechanics, or the first part of physics, is that you usually can say that doesn't fit reality, right? And so that's a nice thing. You can kind of check it at the end. So sometimes at the very beginning, you kind of mess up your signs. That's fine. We all do it. That's not a problem. But just be aware what you get at the end. So let's put the acceleration as a negative number, right? So the number here, 2.10, right? So this number is negative 2.10 times 10 to the power of 4, right? Double check, meters per second squared. Right, that's the number that needs to go in, and then time is given here, so 1.85 times 10 to the minus 3 seconds. Okay, we'll get back to units in a second just to check that that's correct. Okay, so we have 0, we have a negative here, right? So notice there are two negative signs here that should cancel, right, and become positive. So the initial velocity here comes out to be positive, right? So do this yourself. Make sure you're checking me. Don't just trust my word for it. You clearly do this yourself with your calculator and type the numbers out and make sure it comes out to the same value. So you should get 38.85 meters per second, right? So it comes out positive because that's what we expect, right? With the way we set this up, we assumed moving to the right was positive, right? So it comes out with a positive number. If you didn't account for your signs correctly, you might get a negative number here, so then you kind of come back here and you have to think about, well, does that make sense that in the beginning it was moving to the left? No, right? So you have to think about how you set this up, and the way you set this up, everything's now consistent. You get what you expect to get, right? Which is about 38 meters per second. Do a quick check of units always, right? So notice that we put in the numbers, we got some number, and you can convert this to something else. Maybe you're not as familiar with meters per second, so maybe you want to convert it to miles per hour or kilometers per hour and see if that makes sense for a ball moving, right? And the other thing you can do to check if you did this correctly is to check on units, right? So velocity, standard units for velocity, I'll use these brackets to indicate their units we're dealing with, not variables. So meters per second, on the left-hand side of this equation, we should get meters per second, and that should equal to, right, we have a final velocity, so that should be meters per second as well. And then we put in an acceleration, meters per second squared, and then the time was in seconds, right? So notice that you have consistency, right, on the left-hand side and the right-hand side. So on the right-hand side, seconds cancel, right? So this is really meters per second, and then meters per second on the left-hand side too. So that should be the case. If you're doing something with an equation, the units have to work out so that what's on the left-hand side is what's on the right-hand side. If you take meters per second, you can't subtract seconds from it, right? So that wouldn't make sense. If you're taking meters per second and you're subtracting a number from it, it should also be meters per second. So this is something you can do at the very end of solving a physics problem, is to just double check that the units come out correctly, right? And if your units don't come out correctly, that's an indication something's wrong, right? And so that should help you solve these problems better by going through all this process. So notice it's a problem, relatively simple problem, but when we're starting off, spend a lot of time just thinking about, okay, what am I doing? What's the process here? Because, as I mentioned in the beginning, the ball and the mitt are not as important as there's an object moving and another object that's actually colliding with it, say, stopping it. So that concept can be generalized to other things. I mean, it could be a car that's traveling and strikes a wall, right? There's an accident, something like that. So the scenarios can change, but the kind of the underlying physics doesn't change, right? So there are certain general concepts that you can apply to lots of different circumstances. That's what we're after, right? You want to be able to understand the general process when solving these sorts of problems. And so hopefully going through this very, very slowly, step by step, drawing a picture, identifying a big idea, right? At the end of the process of solving the equation, you put in the numbers, you check units, right? So there's a process to be followed, and hopefully if you follow this, you'll find that you'll get better at solving problems, you'll get faster at solving these sorts of problems. Okay, so that's it for this one. Try to make more of these, hopefully, to show you all the steps that I would kind of think about, laying them out one by one so that you can see the process behind this.